Welcome to all. In the previous video, we have solved the numerical problems on the cantilever beams. Now we'll move to the next type of beams, that is fixed beams. Fixed beam means both sides are firmly fixed. So we'll take an examination problem. For the beam shown in figure, determine the displacement at node 2 and internal loads. Take Young's is 200 GPa and breadth is 0.2 meter and height is 0.4 meter. So now this is the beam they given, fixed beam. At the beam they are given the node numbers also 1, 2, 3, 3 points they given. At point 2 the point load is acting, and also this is called as couple or moment, that is 20 kilonewton meter is acting, and the distance between this between 1 and 2 is 3 meter and 2 and 3 is 3 meter. So using this we need to find what is the displacement at this point, displacement as well as internal loads. Internal loads nothing but shear force and bending moment at the each point. So as usual, first step we need to convert into FEA model. So let's divide with respect to the same point only. We are going to divide into two elements, and also here at node 1, node 2, node 3, and the corresponding nodal displacements are V1 theta 1, V2 theta 2, and V3 theta 3, and this is the nodal forces, that is point load and moment F1, M1, F2, M2, 3, M3, and this is L1, L2 equal to 3 meter. Now here Young's pulse is given 200 GPa. Let's convert into everything in a meter. So that's 200 GPa. It is nothing but 210 into 10 raised to 9 Newton per meter square. Now breadth and height is given because they are not given moment of inertia. So that means that this cross section in a rectangle cross section. Therefore we need to find the moment of inertia based on the rectangle section. The formula is BH cube by 12. So substitute these two value and you'll get 1.067 into 10 raised to minus 3 v2 power 4. And also here the force is given, this corresponding at point 2. Therefore F2 is now 10 kilonewton, that is minus, because downward force we consider as minus. Therefore we consider as negative 10 into 10 raised to 3 Newton, convert into Newton. And also couple that is M2. At this point the M2 is acting, M2 is in a counterclockwise. So counterclockwise direction we consider as positive. Therefore M2 is equal to 20 into 10 raised to 3 because we convert into Newton, in Newton meter. Now using this as usual procedure, first we need to find the element stiffness matrix. For element 1, K1 is equal to EI by, so in place of L we need to substitute the L1 value. Substitute the E value, I value as well as L1 value, that is 3. Now we substitute and simplify this. So you will get like this 8.3 into 10 raised to 6, and this is the K1 for the element 1 in stiffness matrix. So this is with respect to V1 theta 1, V2 theta 2 with respect to node 1 and node 2. Similarly K2. So here E also same, I also same, as well as length also same. Therefore we can call it as K1 equal to K2 as usual. But the thing is here corresponding node numbers that is going to change, nodal displacement, which is with respect to element 2 with respect to node 2 and 3. Therefore this is V3 theta 3. So so this is V2 theta 2 and this is V3 theta 3. Now we find out the individual stiffness matrix. We need to find the global stiffness matrix, that is K is equal to K1 plus K2. As usual you had it, therefore you will get a 6 cross 6 matrix. This is the K, global stiffness matrix. Now so only here the terms are going to be added, rest of the terms are as usual. You can keep it. Okay, here 12 plus 12 becomes 24, and here it is 0 and it is 0, again 36 becomes 72. Now global force vector we need to find. So the global force vector we are going to take it for the both, including the both element. It is subjective point load as well as a couple. Therefore F1, M1, F2, M2, F3, M3 with respect to node 1, node 2, node 3. So F1 is 0, M1 is also 0, but F2 is given, that is minus 10 into 10 raised to 3, and M2 is given, that is couple in the clockwise, therefore positive 20 into 10 raised to 3. F3 as well as M3 is as usual 0, 0. Now we need to find calculate the global displacement vector also, that is delta is equal to V1 theta 1, theta 2, V3 theta 3, it is unknown. Therefore finally we need to substitute in equilibrium equation, that is K delta is equal to F. I will substitute this value later. Now I am going to apply the boundary condition using elimination approach. So in this can observe that this is a fixed beam, both ends are firmly fixed, therefore there is no displacement in this between node 1 and node 3. Therefore corresponding nodal displacement V1 theta 1, V3 theta 3 is 0. So therefore eliminate the corresponding rows as well as columns. Now according to that, now you K delta is equal to F, substitute the global stiffness value, global nodal value, displacement as well as global force vector. Now V1 first row first column, theta 1 second row second column, V3 that is fifth row fifth column, and theta 3 sixth row sixth column. Eliminate. So what is left? 24 0 0 72 into 8.3 into 10 raised to 6 is equal to V2 theta 2 is equal to minus 10 raised to 3 into 20 into 10 raised to 3. On solving this, you can get the vertical displacement is minus 50.2 10 raised to minus 6 meter, and vertical and also slope at the node 2 is 33.47 10 raised to minus 6 radian. Now this completes the first question. The second question is internal load. Internal load nothing but, as I told, shear force and bending moment we need to calculate. So for the individual element we need to take, first we'll take for element 1. So shear force and bending moment, element 1 belongs to node 1 and node 2. Therefore with respect to node 1, shear force and bending moment both are there. Shear force, bending moment, shear force, bending moment acting at node 2 is equal to K into delta for element 1, K1 delta 1. We already found out what is K1. You substitute that global stiffness, not global, element stiffness matrix for the node 1, element 1 as well as delta 1. Delta 1 it is belong to the element 1, that is V1 theta 1, V2 theta 2 that we have to substitute. We know V1 is 0, theta 1 is 0, V2 we find out at minus 50.10 raised to 6, and theta 2 is 33.47 into 10 raised to minus 6 radian. So that value you have to substitute here. Now you have to multiply this. If you multiply this, then you will get this. Shear force at node 1 is 10 kilonewton, bending moment at node 1 is 12.5 in terms of kilonewton meter. In terms of 10 raised to 3 you will get that are directly written as kilonewton meter. So keep this in mind, the unit of bending moment is Newton meter, shear force is Newton, and shear force at node 2 is minus 10 kilonewton, and at node bending moment at node 2 is 17.5 kilonewton. Similarly, we need to find the shear force and bending moment at node element 2. Element 2 means here belongs to 2 and 3. Therefore, shear force 2, bending moment 2, and shear force at node 3, bending moment at 3 is equal to K2 into delta 2. K2 we already find out that is element stiffness for the K element 2 that we substitute, and delta 2 nothing but V2 belongs to V2 theta 2, V3 theta 3. So V2 we know, theta 3 know, V3 theta 3 theta 2, V3 theta 3 is 0 according to the given condition, end condition. Therefore if you multiply these two matrix, so you will get shear force at node 2 is 0, bending moment at node 2 is 25 kN meter, shear force at node 3 is 0, and bending moment at node 3 is minus 2.5 kilonewton meter. So this completes the problem. 10 marks problem is a very important one.